X-rays Part D, the sequel. Um, what this notes start out at saying is about an essay. The reason I listed that is on AP exams for the two kiddies. I've seen them ask you to write essays explaining the setup, historical significance of certain modern physics type of experiments. The photoelectric effect, we hit that pretty hard. I'm hoping you guys are able to explain that. The Compton effect is what we will learn about today. That Davis and Germer experiment is one that I drew a little while ago. It was the one that showed that electrons were able to behave as waves. That was the folks who were investigating the de Broglie calculation. Remember, de Broglie is the one that told us that everything has a wavelength. And that wavelength is equal to h divided by mv, the momentum of something. And it was a very, very, very small number. That was the wavelength of a unicorn. But anyway, what I would recommend doing is reminding yourself of those. What I could or you would do is just go to YouTube and type in de Broglie wavelength or Davis and Germer or photoelectric effect. There's all kinds of people who have video tutorials on that, who there's animations made, there's all kinds of stuff. So I recommend taking a gander at those as you're going through your notes too. But right now we will then go straight into Compton, because we are going to take a look at our Compton effect. I forget who it's named after, but I think it was in 1922, the setup of the Compton effect experiment. Very, very, very similar to Rutherford's gold foil experiment. Remember, Rutherford shot what are called alpha particles at a very thin piece of gold foil, and then measured where those alpha particles ended up after going through the gold foil. Similar here, only instead of shooting alpha particles, this dude shot X-rays into a film that's made out of carbon. What he noticed was those X-rays changed their direction. They didn't go straight through, and they didn't bounce directly backwards the way some of them in Rutherford's experiment did. They changed their direction, and hopefully you can tell I kind of did this on purpose. After they passed through that strain or that thin film of carbon, they have longer wavelengths. And please remember, longer waves have less energy in them. They had something called a spectroscope. They used a diffraction grating to measure wavelength. You guys know how those work. Those were the magic squares that we looked at to see the rainbow. But anyway, they were able to very easily measure the wavelength of these X-rays. So what the Compton effect is, well, gosh, X-rays seem to lose energy as they pass through a thin film of carbon. They lose energy. The way we know that is they always have a greater wavelength on the other side. So what they were thinking is, well, gosh, these things change their direction and lose energy. Well, maybe it's because they bumped into something. So let's go looking for something that they could possibly be banging into. And so if these things, by just convention, we draw them being deflected upwards, let's see if there's anything that gets deflected downwards. And so what they did is they modified that setup, and they said, well, let's put some sort of detector down here that we can rotate and move in different places to see if we can detect something that's bouncing off, deflecting in that direction. And obviously they found some things. That's why we're talking about it. Remember, if this gets deflected upwards, that could get deflected downwards. We can detect. They ended up being electrons, and we can get wavelengths here and an electron detector down there to say, those suckers must have been knocked off by the X-rays. All right, there was probably some sort of physical collision between those items. So the deflected X-ray, again, had a wavelength greater than the original. Remember, the longer wavelength means less energy. So a longer wave, they lost energy, and the electron was knocked off at an angle. So their thinking was it's got to be in some sort of elastic collision, just like the types of momentum when we had something going that way and it bangs into something else and this gets deflected downwards and then the original something gets deflected upwards. That type of collision, that type of math is exactly the same thing we're going to do with this guy. They can measure the energy of the incoming X-ray. It's just HF. They can measure the energy of the X-ray after the collision. It's just HF. Different F. So then if there's some energy in that electron that got knocked off, since electrons have mass and they're moving, this is a simple kinetic energy equation, 1/2 mv squared. So this change in energy, the change in energy of the X-ray, ought to equal the energy of the electron. Change in, I should say, sorry. And so the change in energy is HF2 minus HF1, final minus initial, and that ought to equal the change in energy of the electron, which is 1/2 mvf squared minus 1/2 mvi squared. The initial velocity of the electron is 0. So the change equals the change. That sounds pretty fun, damn mental, doesn't it? And that's what it is over here. The amount of energy in that photon in the X-ray becomes the amount of energy in the other X-ray plus the kinetic energy of the electron. All right. Please remember another way to say the letter F, because the velocity of a photon is considered c, which is F lambda. And again, to isolate the letter F, it can be c over lambda. So wherever you see HF, it could be HC over lambda. All right. Now, that energy works fine. But if we're going to start measuring angles, then we need to have something that has direction. Remember, energy is a scalar. It is not a vector. So energy doesn't have a direction associated with it. However much energy you have, you have. Momentum is a vector. It's like some of you. It has direction. And this type of drawing here is the momentum calculation basis, where you put these two arrows tail to tip to equal that one. Then the math would be, I don't know, the energy or the momentum, sorry, of the photon, momentum of the electron, tail to tip, boom, equals the momentum of the original photon, the original X-ray. So that type of drawing is what they're going to now recreate and talk about conservation of momentum. Momentum is abbreviated with the letter P, and so the amount of momentum that light particles have is energy over the speed of light. Remember what we said before. Don't let the fact that photons don't have mass prevent you from calculating their momentum. What momentum is mass times velocity. Okay, you remember that. Einstein told us that energy is equal to mc squared. C is velocity, like I said up there. Well, okay, if I take that mc squared and divide it by a c, I'm left with mc. That means I'm left with the mass times the velocity. That's momentum. To keep it equal, I'm going to take the energy of that photon and divide it by c. And so the energy divided by the speed of light is the momentum of a photon. So the energy of a photon divided by the speed of that photon, which c of a photon is redundant because all photons travel at the speed of light, is equal to mc. All right, the energy divided by its velocity is the momentum. Remember, sometimes energy is replaced with hf. So it could be written as HF over C. All right, so I will do that down here. It could be HF over C. And remember what I said before, that frequency can be rewritten as a C over a lambda. So where that letter F is, I'm going to replace it with an HC over C lambda. Those C's die, and what we learned before the Great Plague was H over lambda is the momentum of a photon, what I jokingly call the MOFO. H over lambda is the mo of a photon. All right? So what we can have is, in the same, H over lambda is the same thing as E over C. It's right there. E over C is the energy of a photon divided by the speed of a photon. H over C, or HF, is the energy. Divide that by C is the same thing as H over lambda. So this is the logic there. I have this photon coming in. It bangs onto something, gets deflected downwards. The energy goes, or the electron, I'm sorry, could be deflected upwards. The electron has mass, so I'm going to call its momentum mv. And that mv has an x and a y component. The the X-ray we have being deflected downwards. It's just by convention. This goes up, that goes down. So that's a phi or a phi. The direction that the electron gets scattered is called theta. So in the x direction, how much momentum is there? Well, the energy incoming divided by c. Again, that's the energy of a photon divided by the speed of the photon. That's the mc. That's what's coming in. This could also be written as h over lambda incoming. It's the same thing. That then is mv cos theta. So the mv cos theta, that's the electron. mv cos theta, that's the x component of the momentum of that electron. The x component for the momentum of the photon now is that energy over the speed of light, which again is the same thing as an h over lambda down here, times the cosine of its corresponding deflection angle, which they have listed as phi or phi. All right? So the x direction, you use cosines. Then in this diagram, you know, these things also both have y components of momentum. One's pointing down, one's pointing up. And since there was no y momentum coming in, there will be no y momentum going out, because these two arrows will add up to my life. Absolutely nothing. So the y component of the electrons, tail to tip, to the y component of the photons will add up to nothing. And the only thing different is you change the cosine to a sine. And then this particular formula is the change in wavelength of those incoming photons. That is what's called the Compton shift. The change in wavelength then becomes this calculation, h over the mass of an electron times c, the speed of light, multiplied by 1 minus the cosine of the angle of the scattered X-ray. So if you know that angle of the scattered X-ray, all of this stuff stays constant. That will give you the change in wavelength of that incoming X-ray, and X-rays then behave like particles. They have a momentum. They can experience 2D mo the same way we did two-dimensional collisions last year. It's exactly the same thing. And so this is some questions from the Blue Book, chapter 27, numbers 16 and 42 that deal with this. Then there's a handout also that I pointed to on our introductory video when I just said aloha to you. That's a handout entitled Compton Shift. See if you can get through question numbers 1 and 2 on those guys. Or 422, question number 3, or 433, I think, or 32, sorry. It's the one entitled Compton Shift, all right? I'm reaching 15-minute Maximus, so I'm sorry again, we don't have physics together, but I love the smell of physics in the morning, and yay, physics.